Hello everyone, welcome to EEEE Lecture number 43A. Today we are going to start with module number 4.1, that is based on transformer. So in transformer we will be studying about its construction principle, then the EMF equation of the transformer, that's quite important, losses in transformer, then the equivalent circuit of an ideal and a practical transformer, followed by voltage regulation and efficiency of the transformer, and finally the most important topic, that is phasor diagram of a transformer at various loading conditions. Okay, so let's get started. So we'll be talking about a single phase transformer. Now this is the symbol of a transformer, right? It's like an inductive coil, two inductive coils, and in between there is a core. So these two parallel lines indicate it's an iron core. And if two parallel lines are not present over here, that means it is an air core. Now we have a primary winding, this is the primary winding and this is the secondary winding. Input is a AC voltage, let us call V1, and output is also a AC voltage. Alright, so let's see what the transformer means. So transformer is a static device by means of which electric power from one circuit can be transferred to another circuit without changing the frequency. Okay, so that's the basic definition of a transformer. Transformer can raise or lower the AC voltage in the circuit with a corresponding increase or decrease in the AC current. And the transformer works on the principle of mutual inductance. So basically, this transformer, which I have shown over here, it converts. So let me write over here. Transformer converts AC voltage into another AC voltage. So basically it's a AC to AC converter, where input is a AC quantity and output is also is a AC quantity. There is nothing DC involved in a transformer. Alright. So a formal definition of a transformer is: a transformer is an electrical device that use electromagnetic induction to pass an AC signal from one circuit to another, often changing the voltage and the current along with it. Alright, so that's the introduction to transformers. Let's move on to the working principle of a transformer. Alright, to the right of your screen you see an entire construction of a transformer. So here we have a transformer core, the grey in color, is the transformer core. Alright, along the transformer cores, two windings are been wound. Now the red winding is the primary winding and the blue one is the secondary winding. Alright, now it works on the principle of electromagnetic induction. So a magnetic flux will be linking both the coils. Now both the coils are isolated, physically isolated, but they are linked by a common mutual flux. Alright, the number of turns of primary windings are N1, number of turns of secondary windings are N2. Primary current is I1, secondary current or a load current is I2, and input V1 is the primary voltage, which is the AC voltage, and output voltage or a load voltage is this is load voltage. Alright, let me add over here, this is load voltage, not current. Alright, so V2 is my AC secondary voltage, or we can call it load voltage. Alright, so this is all it contains. So basically transformer consists of two inductive coils. Now this is the primary winding or a primary coil, we can call it as a coil or a winding, and a secondary winding, which are placed on a common core. So this is my transformer core. The winding or a coil in which the electrical energy is fed is called as the primary winding. So here you apply a electrical energy which is AC in nature, and the other winding from which the electrical energy is drawn out is called as the secondary winding. Alright, so this is the primary winding and this is the secondary winding. So whenever the AC voltage of V1 is applied to the primary coil or the primary winding of a transformer, a AC current I1 flows through it, producing an alternating flux in the core. Now this flux, which is denoted by green color phi, links with the primary winding, and according to the Faraday's laws of electromagnetic induction, EMF, I'll write it over here. Let me expand it. So according to the Faraday's laws of electromagnetic induction, EMF E1 is induced over here. Let me increase the little bit font size. Yeah. So EMF E1 is induced in the coil as per Faraday's law. Alright. So this EMF is induced in the primary coil. Now, assuming that the whole flux produced by the primary winding links with the secondary winding, EMF E2 is produced in the secondary winding. Alright, again, E1 is the self-induced EMF, while E2 is the mutually induced EMF. Alright, so let's go into detail of it. I hope this is clear. So yeah, that's what we were talking about, that whenever a AC voltage V1 is applied to the primary winding, a AC current I1 flows through it, producing alternating flux. Now, when this alternating flux links with the primary winding, as per Faraday's law, EMF E1 is induced, which is given by the following formula. So let us write it down. You all also can write it down. So E1 will be given by E1 is equal to minus N1 d phi by dt. Alright, d phi by dt. So this is the formula. Let us call it, the unit is volt. Okay, let us call this equation number 1, and let me highlight it. So as per Faraday's laws of electromagnetic induction, because of alternating flux linking with the primary winding, EMF E1 is induced in the primary coil. Given by this formula, E1 is equal to minus N1 d phi by dt. And what is N1? N1 is the number of turns of the primary coil. So N1 is the number of primary winding turns. Alright. Turns in the sense, if this is the primary winding, this is number of turns, 1, 2, 3, 4, 5, let's say. So the N1 over here is 5, for example. Okay. Alright, so this is the primary winding, let's say. So this induced EMF E1 in the primary winding is nearly equal to and opposite to that of V1, voltage V1. Okay. So that means this induced EMF E1 is equal to, okay, it's almost equal to but opposite to V1. So they are equal in magnitude, E1 and V1 are equal in magnitude but opposite in sign. So as it is evident from here itself, right, E1 is negative, so your applied voltage V1 is equal to and opposite to the induced EMF E1. Alright. So basically in summary we can say that E1 is basically minus of V1. They are equal in magnitude but opposite in phase. So assuming the negligible linkage flux, almost the whole flux phi produced by the primary winding links with the secondary winding. So what are we assuming? That this whole flux, this green color flux which is linking the primary and the secondary winding, is entirely linking the primary to the secondary winding. Alright. So therefore a EMF E2 is produced in the secondary winding. Alright, because the primary winding alternating flux is linking the primary winding to the secondary winding, so a EMF E2 is produced in the secondary winding, and thus E2 EMF is called as a self-induced, is called as a mutually induced EMF. Alright, and voltage E2 is given by the formula E2 is minus N2 d phi by dt, again d phi by dt. Alright, the unit is volts. and this is formula equation number 2. Let me put it inside the box. And what is N2 given by? What is N2 basically? Let me save the file. Yeah. So this is my secondary induced, mutually induced EMF. So from above discussion, E1 is the self-induced EMF, while E2 is the mutually induced EMF. Alright. Now, if the secondary winding is closed to the load, okay, it's not open, it's closed to the load, then a current I2 flows to the secondary winding. So therefore we can say that the energy is being transferred from the primary winding to the secondary winding. Alright. So that's why the transformer transforms the electrical AC energy, AC voltage, into a AC voltage itself at the secondary output. Now that AC voltage might be lower than the applied voltage, or it can be greater than that. So from equation number 1 and 2, which we have written over here, E1 is minus of N1 d phi by dt, E2 is minus of N2 d phi by dt. Alright, so that is what we have written. And if we take, let's say, if we divide E1 by E2, what do we get? We get N1 upon N2, and this is called as the transformer ratio K. Okay, N1 upon N2 is the transformer ratio K. So this I can write it down. Transformer ratio denoted by capital K. Alright. Now, if N2 number of turns of secondary winding is greater than N1, then we can say E2 is greater than E1. Okay, if N2 is greater than N1, then E2 is greater than E1, right? Or else we can say that the K is less than 1. Alright, if N1 is less than N2, then K is less than 1. As you can see here, the secondary windings are more than the primary winding. So this type of transformer is called as a step up transformer. So what does the step up transformer do? Any applied AC voltage, it will raise the voltage. So let's say, for example, if V1 voltage is 100 volt AC, it will convert it to, let's say, 300 volt AC. Okay, this is an example I'm giving you. So transformer which steps up the voltage, applied AC voltage, to a higher value at the secondary winding is called as the step up transformer. Similarly, if N1 number of turns is greater than N2, right, then such a transformer is called as a step down transformer. Alright. If N2 is less than N1, then E2 is less than E1. That means K is greater than 1. In this case, transformer ratio K is greater than 1. So whatever applied input voltage, let's say input voltage is 230 volts AC. Okay, it will step it down to a lower value, let's say around maybe 20 volts AC. So a transformer which steps down the applied AC input to a lower value AC at its secondary, it's called as a step down transformer. Okay, so these are the two types of transformers which we have. Alright, it is clear. And remember this ratio, transformer ratio, E1 upon E2 is equal to N1 upon N2 is equal to K. That's very important. Alright, let's move on to the next topic. Okay, so let's see the construction of the transformer. Now let me concentrate on this. Okay, so let's begin. So a transformer mainly consists of iron core. Now this is my, let me just slightly reduce it. Yeah, this is my main iron core, or we can call it as a steel core, this entire thing. Okay, these are laminated steel cores, laminated steel sheets which have been joined together to form the actual core of the transformer. So transformer mainly consists of an iron core, primary winding, and a secondary winding worn over this core. Okay, So what is this core? A core is a rectangular in shape and is laminated. Okay, so that means whenever a core is carrying an alternating flux, loss of energy might take place, and that is due to the eddy current loss. Okay, so therefore steel is used for the manufacturing of the core, which is a high grade steel, which will reduce this hysteresis or the eddy current losses. All right, so that is about the core. Okay, and what material it is made up of. Next is the winding, the two windings, the red color and the blue color. The red one is called as the primary winding and the blue one is called as the secondary winding. So one winding, the primary winding, is connected to the source of the electrical energy, while the other winding, the secondary winding, is connected to the load. Okay, so this will be going to the load. Alright, each winding is properly insulated from each other. They have no physical connection between them at all. Alright, so each winding is properly insulated from each other as well as the core. Now, depending upon the core and the winding arrangement, the transformer construction is classified as a core type transformer or a self type transformer. Okay, so these are the things which we have written. Whatever I've said, I've written over here. So yeah, windings. Yeah. So depending upon the core and the winding arrangement, the transformer construction is classified as core type and cell type. In core type, the two parts of each winding are electrically connected in series. That means here a winding encloses the whole core. And this arrangement will give you good magnetic coupling between the primary and the secondary winding. So normally your core type transformer are preferred. Okay, for transforming high voltage transformers, high voltage, right? For transforming high voltages, we prefer the core type of transformer. So that's about the construction of the transformer. So this we have to start with that, what the transformer consists of: iron core, primary winding and secondary winding. And then we'll talk about the core, why it is laminated sheets, it reduces the eddy current and the hysteresis losses. And then we have talk about the primary winding and the secondary winding. All right, so let's move on to the next topic, that is EMF equation of a transformer. Right, so let's concentrate on this now. So here I have drawn the symbol of a transformer showing the primary voltage V1, secondary voltage V2, primary current I1, secondary current I2, and E1 and E2, which are the induced EMF. Okay, E1 is the self-induced EMF and E2 is the mutually induced EMF. N1 and N2 are number of turns of the primary and secondary windings respectively. So normally a AC voltage is applied to the primary winding. So over here V1 is applied with a sinusoidal AC signal. Okay, this produces the flux, the alternating flux in the core, which also varies sinusoidally. Okay, so let us see that the equation of the sinusoidal AC flux in the core will be given by the following formula. It is given by phi equal to phi m sine omega t. So that's the equation of the alternating sinusoidal AC flux. Okay, so as per the Faraday's laws of electromagnetic induction, the self-induced EMF in the primary winding is given by E1. All right, so E1 is given by minus N1 d phi by dt, which is we have seen before, right? Now what is phi? Phi m sine omega t. So we have to differentiate that term. So we'll get minus N1 d by dt of phi m sine omega t. All right, and the integration of this will be, the differentiation of this will be minus N1. Phi m is a constant, and differentiation of sine omega t will be cos omega t. All right, is this clear to you? Yes, and therefore the equation will be E1 is equal to, if I want to cos omega t, I can write in terms of sine also, sine omega t minus 90 degree. All right, all right, so E1 is minus N1 phi m cos omega t, which can be written as, if this is has to be written positive, n1 phi m, and we can write it as sine of omega t minus 90 degree. Okay, if we want to make it positive and we want to write in terms of sine, that is what we get. All right, let me put it inside the box. Okay, all right, let me call this equation number 4. So from equation number 3 and 4, it may be noted that the self-induced EMF E1 lags behind the flux phi by 90 degree. Okay, so it's very clear from equation number 3 and 4 that E1 and phi, which is the which is the main flux, okay, E1 lags behind the flux by 90 degree. So this is an important point to remember. Okay, so let me highlight this. EMF E1 lags behind the flux phi by 90 degree. This will be helpful while we draw the phasor diagram. All right, so let's move on now. Now, comparing equation number 4 with the standard sinusoidal form. Okay, the standard sinusoidal form is E equal to Em sin omega t plus or minus phi. Now, the maximum value of the induced EMF will be given by. Okay, so what is the maximum value of the induced EMF? We can write it down over here. Em. Okay, let's call it Em. Maximum value of the induced EMF is N1. Okay, we have made one mistake over here. Derivative of sin omega t is omega. Omega also will come over here. So in this formula, we have into omega. Omega is also there. Okay. All right. This is equation number 4. Okay. So now, if you see, compare equation number 4 with this standard form of Em sin omega t plus or minus phi. What is Em? N1 phi m omega. Okay, is it not? Rest is sin omega t minus 90 degree. Okay, so the maximum value of induced EMF is N1 phi m omega. Let us call this equation number 5. Alright, let me put it inside the box. Therefore, the RMS value of the induced voltage in the primary winding is given by. What is the RMS value given by? E1. Let's say E1 is the RMS value in the primary winding. It is given by Em by root 2. And what is Em? N1 phi m. And omega we can write it as 2 pi f. So let me write it as 2 pi f, and this is divided by root 2. Now let's call this equation as, we will be calling it soon. Yeah. So let's take out your calculators and find out what is this equation. E1. N1 2 pi upon root 2. What is 2 pi upon root 2? You can calculate 4.44 it will be. It 4.44 into F into N1 into phi m. So that is my RMS value of the induced EMF in the primary winding, and let us call this equation number 6. Okay. Similarly, the RMS value of the induced EMF in the secondary winding also will be given by similar formula. Okay, I will tell you the difference, but let us finally write over here what is phi m, where phi m is the maximum flux denoted in Weber. Okay, and F is the supply frequency. I hope you know what is N1. N1 is the number of primary winding turns. Okay. Similarly, the value of the induced EMF in the secondary winding is given by the following formula. Okay, we need not need to derive it. We will write it over here. E2 is equal to 4.44 F N2 phi m. Alright, let me put it inside the box. If you follow the same trend, it will be as follows. So, E1 and E2 are called as the EMF equations of the transformer. Okay, alright, we have derived for E1 and similarly we can write for E2. Equation number 6 and 7, that is E1 and E2 expressions, are the EMF equations of the transformer. And if they ask you in the exam, you have to write up till here. Now, further, a little bit of observation which is there. If I divide E1 by E2, what I will get, E1 is 4.44 F N1 phi m, and what is E2? 4.44 F N2 phi m. So what's cancelled out? It's very obvious now. 4.44 frequency and phi m will cancel out. So what is remaining over here? Remaining is, that is E1 upon E2, okay, is given by N1 upon N2. Alright, E1 upon E2 is given by N1 upon N2. Alright, and if I want to write it reverse, let's say E2 upon E1 will be given by N2 upon N1, and that we call it equal to transformer ratio. I think earlier we have defined a transformer ratio that was N1 upon N2, but this is the final one. Okay, so this is the transformer ratio which we have, the formula. This is the correct one. This is called as transformer ratio, and it is denoted by K. Earlier I guess we have also written a transformer ratio. Let me correct that. Yeah, I think this was N2 upon N1. Okay, so let me correct this. This will be E2 upon E1, N2 upon N1 is K. Okay, so just a minor correction. Now let's get back to the topic. Okay, it is loading a bit. Let's wait. Yeah, this is the transformer ratio. Alright. So now, neglecting the small primary and the secondary voltage drop. Okay. So what we can say, that means we can say that V1 is approximately equal to E1 and V2 is approximately equal to E2. Therefore, the new ratio will be given by E2 upon E1 is equal to N2 upon N1, and that is equal to V2 upon V1. Okay, and that is equal to K. Alright, this equation comes in very much in handy. Okay, that's important. Alright, so if we consider in a transformer, if the losses are considerably negligible, therefore the input and the output can be approximately equal. Okay, so that means what? V1 I1 will be equal to V2 I2. Remember, this is just an approximation. If this is the case, we can write I2 upon I1 is V1 upon V2. Sorry, I2 upon I1 is V2 upon V1, and V2 upon V1 is K. So we have another formula. Okay, considering the losses in the transformer are negligibly small, and therefore the input and the output can be approximated as follows: the input power and the output power. So V1 I1 is equal to V2 I2, and therefore we get this new formula, that is I1 upon, here I have to write I1 upon I2. I1 upon I2 is V2 upon V1, and that is equal to K. Alright, so these are the different forms of transformer ratio. Let me add it over here. So finally E2 upon E1 is equal to N2 upon N1, which is equal to V2 upon V1, but it is equal to I1 upon I2, and that is equal to K. So this is the final form of the transformation ratio or transformer ratio, K, capital K. And for a note, for a step-up transformer where N2 is greater than N1, the K is greater than 1, and for a step-down transformer N2 is less than N1, then K is less than 1. Alright, So this is all about the EMF equation and finally the transformer ratio. Alright. So we come to the end of this lecture. Let us revise what we have done so far. I hope this is clear, right? These are the different forms of the transformer ratio. Let us revise what we have done so far. So we have discussed about a transformer. We have seen its symbol, construction, principle of working, and also we have studied the EMF equation of the transformer. So construction, principle of working, EMF equation of the transformer. Now next we will study about various losses in the transformer. Alright. So yeah, that's it for this session. We will continue the topic further in lecture number 43B.